Good morning. Welcome to Krishna's class. I had to stay away from this lectures for a while because of the throat problem, which disturbed my voice. I'm still not completely recovered from it, but nevertheless, I thought let us make a new beginning. We completed a discussion on what are called Banach spaces in the context of abstract integration theory. Now, we make one more leap and go to the concept of what are called complex measures. Now, let us recall what the measures are that we have introduced already. What you have is a non-empty set, then a sigma algebra, and a measure mu. This is what we call a measure space. And let us see each one of these things. Now, this is a non-empty set, of course. Then you have A is the sigma algebra is a collection of sets subsets of X used to measure the space. Now, what kind of subsets form a sigma algebra? You know that if the following concepts: one, the empty set and X belongs to is one among the collection of subsets. Two, if A belongs to A complement belongs to A. Three, finite union of it's closed under finite union. It is closed under finite intersection and then it is to be a sigma algebra. We need the following also. This is up to this what we have said is just an algebra, and for this to be a sigma algebra, what we need is this, that union infinity and similarly it is closed under countable union, it's closed under countable intersection. Now this is the sigma algebra. This is the basic structure of subsets that we choose to start developing a measure concept on X. Now, so phi and these sets are called measurable sets. So empty set and the whole set is measurable. If A is measurable, the A complement is measurable. The finite union of measurable sets is measurable. Finite intersection of measurable sets is measurable. Countable union of measurable sets is measurable. Countable intersection of measurable sets is measurable. Now this is what it is. This is the structure that we seek for a sigma algebra. Now what is a measure? So we are still not introducing complex measures but real measures. So mu is a function defined on a sigma algebra to extended half length. Okay, that is 0 to infinity, infinity to 0. So it's a real valued function as well as it could take the value infinity. Okay. Now, for instance, on the real line, when you take the whole measure of the real line, it is taken as infinity. Okay. It is measurable and it is infinity. Okay. For intervals, you have the definition of measures, and there are measurable sets. And it is even interesting that there are non-measurable sets. Now, this is the important. Okay. So, this is the nature of the function. Now, what are the properties of this function? So, of course, this means that A is greater than or equal to 0. This is just a restatement of this fact. Now, we have A mu A is less than or equal to mu B. Then you have mu of because you have the mu of the empty set is taken as 0. Okay. So, extending this further, you get mu of mu of AI. Whenever AI intersection for I not equal to 2. Now it is countably or it is finitely additive. Not only that, we also require mu of 1 to infinity AI to be equal to sigma I equal to 1 to infinity mu AI whenever these sets are mutually disjoint. That means AI intersection not equal to J. They are mutually disjoint. So it is countably additive. Not only finitely additive, it is also countably. Now this is the property that is required of a set function which could be called a measure. Okay. So you have got a given set, and on which you have set a set of subsets, and then you have this non-negative real valued map mu, which has this set of properties. Then you say mu defines a measure on X. Okay, and this is a measure space or measurable, not only measurable. The XA is a measurable space, but XA mu is a measure space. Okay, so it's a real measure that we have defined, which is a generalized, as you have seen, while looking at Lebesgue measure and so on, you are already familiar with the fact that this is something that has been evolved out of our concept of length for intervals. Okay, it's a very wonderful idea, which forms a basis of the integration theory. Okay, now having done this, now here also, of course, you see that you have this property mu A is less than or equal to mu B, because these are real numbers, real non-negative numbers, they are comparable. Another remark I want to make is that this is not necessarily finite. This is not necessarily finite. So the countable addition, sigma I equal to 1 to infinity mu AI, need not be finite. It can be even infinite. Okay. Once you take this interval, you take the interval, say n to n plus 1, and take the whole x is okay. You take this interval. I will give an example. You take these intervals. Take the union of this. This is equal to. This is the interval 0 to infinity. Okay. These are mutually disjoint. Okay, and the length of each of this interval is 1, and that is what is called the Lebesgue measure of that interval. And if you take the infinite sum of that, what you get is the following. You get infinite. Okay. So what I mean to say is that this sum that we have, the countable sum that we have written here, need not be finite. It could be infinite also. That is why we define measure as a non-negative set function which can take the value infinity also. Okay, so with this background, now we ask the following question: is it possible to generalize this further? If so, in what direction? Okay, here we have restricted mu to take values on the interval 0 to infinity, both 0 and infinity included. Now instead, we will do one thing. We will start talking about complex functions. Okay, so and with appropriate properties, we would like to call that a complex measure, and we explore how far we can go with this theory under the assumption that mu is a complex measure. Okay, so that's what we want. So we will start with complex measures. So let and script M a set of which format so what we have now is X, which is a measurable space. Now on that, now instead of a non-negative measure, we now introduce a complex measure. Okay. So we make some definitions to introduce to prepare the ground for introducing complex measure. So definition. Let EI be a countable collection of members of then EI is called a partition of E if EI whenever I not equal to J and now this is what is called a partition of it. The condition is that E has to be the union of the sets EI. Apart from that, we also have each EI intersection EJ is empty whenever I is not equal. So they are disjoint class of sets whose union is equal to E. This is the meaning of that. So this is what you call a partition of. So we use the word partition in this context. Now we define a complex measure. Complex measure. A complex measure on the sigma algebra M is a set function C such that mu of E equal to mu of EI for E measurable and EI with partition. Now it's a complex valued function associating with each element of the sigma algebra, a complex number, with the property that it is countably additive. It's important. It's countably additive. Okay. Now, what are the consequences of this and how this differs from a real measure? Now, one of the things that you should realize here is that there is no order relation there does not exist an on C. There is no order structure. Order structure on C. Now this will be reflected automatically because you recall that when we were talking about real measures, we had, because for real numbers there is an order structure, and therefore if A is, we had the relation we had was A, B are, this is what we had. But such a relation cannot exist here because there is no, this does not make any sense. Because each are complex numbers and there is no order relation. So that is something that we have to. Now the second point is this, that in the case of real measures, that is positive measures, because we had this infinite sum also accepting a value infinite. Okay. In the case of E of equal to this we had accepted. Whereas such a, this is not possible in the case of complex measures. on the other hand, so the possibility was this series could either converge or diverge. That is the series either converge, because these are all non-negative, or diverge. So that is the speciality of this case. So see, we have E equal to union EI. Now suppose we and the union does not change with the interchanging of indices. Therefore, what we need is that every rearrangement EI converging. Therefore, and this is facilitated if this series is absolutely convergent. Therefore, the series absolutely for every partition that is we require mu of finite. Now this absolute convergence actually sets a bound for this sum. Okay, therefore we shall give a dominating, or we shall identify a dominating positive measure determined by this complex measure. So the problem of finding a positive measure lambda which dominates a is now open. Let us explore this. Okay. In fact, you see that it is certainly going to be something finite. Okay. Therefore, we shall have to find out a corresponding binding, because this is going to be something like lambda less than or equal to lambda. So we will define a real positive measure on the sigma algebra such that this particular property is satisfied. Okay, that is given a complex number, a complex measure M a positive measure a positive measure lambda is said to dominate mu the complex measure mu if so does there exist such a positive measure. That's a question. We shall explore this one. And we would like such a lambda as small as possible. Now, every solution of this problem must satisfy the following condition. Satisfy the following. It is mu e lambda e ei, which is greater than or equal to so this is absolutely convergent. Okay, therefore this condition is satisfied. Means this is the important criteria that it should have for every partition ei of this is the condition that it should satisfy. Okay. Now we define a set function designated by mod mu, just a symbol. It's only a symbol. Okay. Is equal to supremum of ei so let this be the definition. Okay. This is absolutely convergent. Okay. Therefore, you see that for each partition, you this, and then you take the supremum of all this, and that would give you that is defined as sorry, I think the notation is wrong. Okay. Define it this way. Okay, so that's the definition. Define a set function. So this is the definition that we. Now the questions are whether this makes sense or not. Where the supremum is taken over all partitions then we have it is clear. However, in general, not equal to you can give site examples for this. So we define such a set function. Now the question that comes up is this. So this is the definition, and does such a function define a real positive machine? Okay, so the question is, this is what we expect. A measure on this is the question that ask. Okay. Now we shall make some remarks. If it does, which we don't know, we have to prove that it does, and we hopefully prove this. Then it is the minimal solution for our problem. This is the best possible solution for this problem. But if you have any other measure serving this purpose, then that measure is likely to be give a greater value for E than what this absolute mu gives. Okay, that is the meaning of that. Okay. In the sense that if lambda is any other solution, any other measure with the property it means it is a dominating measure for this, but certainly not necessarily the best possible. Now, with this property, we define the set function is or the total variation of called the total variation of E. You also want to make a remark. The terminology of mu x. Now, that is the whole space. It's the total variation of mu over the whole space, whereas it is on E. In general, this is on E. Okay. So the general terminology is total variation. Now, is the total variation sure? That is the question. Now, clearly, The total variation of means itself. Further, finite. This is so. This is because this is true since the following. That is, since and which is less than or equal to this is true. Thus we have the following. 1, well, complex plane actually lies inside some disk. We'll see. Three. Is called a measure of bounded range. With the total variation given by mod mu. Now that, of course, ends the discussion today, and it leaves the following question. That is the one that we want to pick up next, is this. Thus the question that we want to take up is this. Sigma algebra. This is the question. So our next theorem, or the first theorem that we take up in this discussion, is that to prove that this is indeed this is what's called the total variation. The total variation of mu defines a positive measure on. Okay, so that's it. Right. So thank you very much. So I am very happy that we could resume the talk again. We will continue with it. I will be appearing more frequently. Thank you very much.